So before we start our lesson on arithmetic series, let's just do a little review on sequences. So here I have a sequence 1 2/3, 1/3, 4 over 27, 5 over 81, and 6 over 243. So we want to first determine the next three terms of the sequence and then come up with the general term and a recursive formula for the sequence. So in the last two lessons, we talked about arithmetic sequences and geometric sequences. So arithmetic sequence again is that there's a common difference between each of the terms. So maybe that's the first thing we want to try. So the difference between 1 and 2/3 is a negative a third. So it seems like we're going down negative a third every single time. So it looks promising because we go from 2/3 to 1/3. We do subtract a third, so it looks like we might have a common difference of a third. But then at this fourth term, that's where it breaks apart because 1/3 minus 1/3 would be 0. Unfortunately, that fourth term is not a 0. So we can rule out that this is not an arithmetic sequence. So we can try geometric. So what's the common ratio? So going from the second term to the first term, or going from the first to the second, we're going down by 2/3, so multiplying by 2/3. And we can see at the third term that fails already because 2/3 times 2/3 is 4 over 9, which is not 1/3. So this sequence is neither geometric nor arithmetic, so we need to look for a pattern in there. And this one looks tough. So a big hint I would give is that what happens if we convert 1/3 to be 3/9? And of course, the fraction 1 is just 1 over 1. Sorry, 1 as a fraction is 1 over 1. And maybe now we can detect a little bit of a pattern. So in the numerator, we can see that this is going up by 1. So 1, 2, 3, 4, 5, 6. So we can see that the next terms in our sequence, the next 3, 1, might follow that pattern of 7, 8, 9, and in this case, what's our denominator? Our denominator is going up by 3. So in this case, we got 3, 1, 3, 9, 27. So it's going by multiples of 3. And so the next three terms, the denominator of this sequence is 729. And then 729 multiplied by 3 is 2187. And finally, the denominator, the last one, is 6561. So this one's a little bit tricky, but that's the next three terms of our sequence. So how can we define the general term? So general term in this case would be, so we see at the top, it's just going up by 1. So T of n is equal to n. And at the bottom, well, we could recognize that it's just a geometric sequence. So the first term is 1. So remember the general term for a geometric sequence is a times r to the power of n minus 1. So in this case, since a is 1, we don't have to write that. And our denominator is just 3 to the power of n minus 1. So the recursive formula for this, we can say it's something like a of 1 is 1, b of 1 is 1. So that's our starting point, and then we can say that in general, T of n is equal to, and this is where it's a fraction. So again, A is going to represent our numerator, B is our denominator, and we could think of our numerator is, yes, it's going up by 1, but we could just see that as a general arithmetic sequence that's going up by 1 all the time. So in this case, T of n is going to be A of n, the previous term, the previous term's denominator, adding 1, sorry, the previous term's numerator adding 1, and then the denominator is the previous denominator, but we're going to multiply it by 3, and this is for in general when n is greater than 1. So the recursive formula for this one is a bit tricky, so because we just have to break it down into two parts. So I've done that with using a and b, and here we define this sequence recursively. So let's get on to today's lesson. Where we're going to talk about arithmetic series. So the naming of it is weird because we call it series, but essentially we're going to find out that this is a sum. So we're going to define what a series is in general, and specifically what an arithmetic series is. And then once we know that we have an arithmetic series, then we're going to be able to determine what that is. So I found this one day on the internet. It was pretty neat and tied it into a math lesson. So this was a British military fitness red workout. So it was pretty interesting. So this workout consists of three things. The British call it press up. We over here call it push up. The next one's a tuck up. So basically you jump up and then you bring your knees to your chest and you land. And then the next one looks like we call it super crunch, which looks like a combination of a sit up and a leg lift a little bit. So as you sit up, you're pulling your knees towards your chest. So the idea behind this workout, this challenge, is that it starts you off small. So on the day one, you do one of each, which, good start. Then day two, what happens the next day is that you do two of each now. And then on the next day, you do three of each, and then you continue on in this pattern until we look at day 10. Basically, you're doing 10 press-ups, then 10 tuck-ups, and then 10 super crunches. So the question that I kind of came up with was, given over the 10 days, what would be the total number of push-ups, tuck-ups, and super crunches that you have done after 10 days? So we could go through a little pattern or sequence to sort of determine that. And then a bigger question is, well, after 3 months, how many would you have done all in total? So how we might go about doing that. So here we talk about definition of a series. So I'm not sure why this term is called the way it is, but a series is basically the sum of the terms of a sequence. So given a sequence, so in the example we have a sequence 1, 2, 3, 4, a series is the sum of all those terms added together. So in that case, the series of 1, 2, 3, 4 would be 1 plus 2 plus 3 plus 4, which equals 10. So it makes sense that when we talk about an arithmetic series, that's the sum of the terms of an arithmetic sequence. So that's what we sort of discover up above, is that if we sort of go and look at our table, how many of these things, press up, tuck up, and super crunch, are we doing every day? So here we can say that, well, that's being done 3. We're doing 6 there, 9, because each day we're adding one more of each. Since there's 3 things, it makes sense that we're going up by 3s all the time. So there's 12, 15, 18, 21, 24, 27, and finally on the 10th day, we are doing 30 things altogether. So we can see that this is an arithmetic sequence. The common difference is 3, but the question we want to know is, what is the sum of these terms? So let's just break this up, and let's just simply, for 3, 6, 9, 12, and 15, we're doing 3 plus 6 plus 9 plus 12 plus 15. And we all add that up together. I got 3 plus 6 is 9, 18 plus 9 is 18, 18 plus 12 is 30, plus 15 is 45. So basically, after 5 days, we would have done 45 reps of these things. So a little bit about notation. Before we talk about T of n, or T subscript n, we're going to refer to that as the term number of the nth term of a sequence. So in this case, when we talk about series, we denote it by S of n. So S is short for series, and this is basically what's the sum of the n terms within a certain sequence, of the first n terms. So we can see that the problem of determining how many reps were done is actually an arithmetic series. So how can we go off and sort of derive a general formula for this? Because we do it for 5, that's not so bad, but once we get to 10, well, yes, we're going to list off 10 numbers and add them all up. Again, doable, but once we get to 90, that's not so bad. I mean, that's pretty bad. So hopefully we could derive a little algorithm for this. So this is a neat little trick that apparently Gauss did when he was a boy, given a problem similar to this, if not identical. And basically, how can we come up with maybe a general algorithm to determine the series of an arithmetic sequence? So here I listed out what we did above, and what I'm going to do is, so really this is S of n, in this case S of 5, summing up 5 terms, and I'm going to write these terms backwards. So here is going to be 15 plus 9, plus 12. I'm going to write these terms backwards, so here we're going to get 15 plus 12 plus 9 plus 6 plus 3. We know that it's going to add up to 45, so the sum isn't any different. And the reason why we want to maybe do this is we can actually see a pattern here. Well, 3 plus 5, so 3 plus 15, that's 18. So if we sort of add our numbers that are lined up, 6 plus 12 is also 18. 9 plus 9 is 18. 12 plus 6, that's also 18. 15 plus 3, that's also 18. And of course, 45 times plus 45, that's 90. So one thing that we recognize is that when we flip the order of the sequence and we add them up, we get the same values on the bottom. Well, how many terms do we have here? Well, that's going to be 5. So we know that here, this is going to be added up to S of 5 as well. So what we discover here is that if we add the first term and the last term, we add them together, and then we multiply by the number of terms that we have, in this case 5, we're going to get twice our sum. All right, so in this case, if I look at over here, I'm going to take in 5 plus times 3 plus 15, and that's going to be 5 times 18, and we can see that's going to be 90. So how do we get S of n? Well, basically we've doubled it. So in this case, we're going to divide it by 2. So here we come with a general formula that S of n is the first term plus the last term multiplied by n divided by 2. So there's a neat formula that we come up with, and this works in general no matter how long our sequence is that when we add them all up, the formula for the series is S of n is the first term, t of 1, plus t of n, so that should be an n, and then multiply by the number of terms that there are, divided by 2. So here's the formula that we just sort of derived. We could also write this formula another way. So this one's a little bit more lengthy, but notice here, in this one, we don't actually need to know the last term, we just need to know what the common difference is. Well, how do we get one formula from the other? Well, from our arithmetic sequence, we recognize that t of n is equal to a plus n minus 1 times d. So that is, in general, that's where the term is, and that's exactly what we're doing in our original formula. So I actually like remembering the first one because it's easier to do. First term plus the last term multiplied by n and divided by 2. And all we're doing here is that we're using this formula to calculate what the last term is. So here, if we sort of replace t of 1 plus t of n, if we replace t of n with this that we have up here, we get t of 1 plus a plus n minus 1 times d. Well, we know t of 1 is just a. And of course, a plus a is just 2a. I'm just going to move the d to in front of that. And essentially, that's what we've done, is we replace t of n with what we sort of simplified this to be 2a plus d times n minus 1. Okay, so sometimes if we're not given the last term, but we know what the common difference is, we could use that second equation. But to me, because I don't like memorizing, this one makes more sense to me after I saw how it was derived and knowing this one. So this is the only one I need to memorize. It's a little bit more straightforward. I'm always going to calculate t of n first, plug that into the first equation to get my series. So let's go through. this example. So we want to calculate how many reps would have done in total after 10 days and after 90 days. So we just apply our new series formula that we learned. So S of n is equal to n times t of 1 plus t of n all over 2. So we want the first 10 terms, so n is 10. Well, the first term in our sequence was 3. And if we remember in our chart, on the 10th day, we actually did 30 reps divided by 2. So here, S of 10 is, I'm going to simplify 10 over 2 first. That's going to be 5. So 3 plus 30 is 33. So 5 times 33 is, 5 times 30 is 150, plus 15 is 165. So after 10 days, we would have done 165 reps in total. So let's go off and do S of 90. So our first term is still 3. Well, we can go back in the table and kind of continue that pattern and list out the 31st, 11th, 12th, 13th, all the way to 90 days and figure out how many reps we would have done on that 90th day. But instead of doing that, we can just rely on our general term formula for our arithmetic sequence. So that's t of n is a plus n minus 1 times d. So I could have used the other series formula that I showed you before, but like I said, I have a bad memory. I don't actually remember what that is right now. So, but I could remember this one consistently because if we applied it a lot, even just in doing arithmetic sequence. So t of n is a plus n minus 1 times d. In this case, I want the 90th term. First term was 3, so n minus 1 is 89. So 90 minus 1 is 89. We have a common difference of 3. So in this case, we're going to see that this is going to be 3 plus, well, 90 times 3 is 290 minus 3, which is 287. And we see that at the 90th day, which kind of makes sense, we've done 270 reps altogether. So I can fill that in now, all over 2. So 90 over 2 is 45. And 3 plus 270 is 273. And we take 45 and multiply it by 273. We get 12,285. So after 90 days, if we did that workout, we would have done a total of 12,285 reps in total, which is pretty impressive. I mean, doing 270 altogether, 30 of each thing, 90 of each thing on that 90th day, that's a pretty intense workout. So this is what this unit is actually, or this section is actually all about, just dealing with arithmetic series. Again, it's just adding up all the terms within arithmetic sequence and really applying the formulas that we have up over here. That we go through is here we're given what to calculate the first 10 terms. We're given the first term, we're given common difference, and we're given the 10th term. So in this case, I don't really care what the common difference is. S of n, again, is n times t of 1 plus t of n over 2. So in this case, we want the 10th term. And we know what the first term is, 2. We're happy to be told what the 10th term is, which is 38. All over 2. So this is really 5 times 40, which is 200. So the sum of the first 10 terms of that sequence would be 200. The second one, so here we're just given a of 1, the first term, and the common difference. Write a formula. So a is n times t of 1 plus t of n all over 2. So we're still calculating for the 10th term. So we don't know what that is. But we do know what n is. N is 10. So the first term was 1. So I could use the other formula that I showed you, the second part. In other words, replacing t of n with actual expansion and then getting 2a plus, I don't even remember what it was. So I'd rather just again go off and figure out what t of 10 is. So the equation for that is going to be 1 plus n minus 1, which is 9, and a common difference here is negative 4. So the 10th term is going to be 1 plus or minus 36, which is negative 35. All over 2. So this becomes really 5 times a negative 34. And 5 times negative 34 is, well, 5 times 30 is minus 150, minus another 20, so it's going to be minus 170. So it's the sum of the first 10 terms of that sequence. So in this next example, it's a little bit tricky. So here our series is negative 12 minus 8 minus 4 minus etc. 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 So we want the first 10 terms of this, the sum of the first 10 terms of the sequence. So let's write out the sequence explicitly. So here the sequence is actually negative 12, negative 8, negative 4, dot, dot, dot. So what's the first term of my sequence? A is negative 12. And here, what's the common difference? Well, here we're going up by 4 all the time. So there's going to be plus 4. So we want the sum of the first 10 terms. So again, in general, S of n is n times t of 1 plus t of n all over 2. So in this case, we want the first 10 terms. So n is 10. And the first term is negative 12. So off to the side here, I'm going to calculate what t of 10 is. So in general, t of n is a plus n minus 1 times d. So negative 12 plus 10 minus 1 is 9. And I'm going to common difference here is 4. So that's going to be negative 12 plus 36. So here the 10th term is going to be 24. All over 2. So you're going to multiply 10 over 2 first. That's going to be 5. Negative 12 plus 24 is 12. So 5 times 12 is 60. So here we're going to see that the first 10 terms are going to add up to 60. So these ones are pretty straightforward. Basically, we're just going to have to calculate what the 10th term is every single time. In the next example, we want to determine the sum of this arithmetic sequence. Sorry, the arithmetic series. So what we could detect from this question is that, first of all, we know that the first term is 3. It's going up by 5. So again, we can list off the sequence itself. It's 3, 8, 13, dot, 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 58. So here, the common difference is 5. So we go off and write off our series formula, which is S of n is n times t plus t of 1 plus t of n all over 2. And here, well, the problem here is that we don't know how many terms this is. So we still want to look for the sum. We don't know what n is. Thankfully, we know what the first term is, and we know what the last term is. Well, how do we calculate for n? Well, we know that 58 is the nth term. So we go back to a general term for an arithmetic sequence. So that's t of n is a plus n minus, n minus 1 times d. So we know that the t of n is 58, because that's my nth term. We know what the first term is, that's 3. We don't know what n minus 1 is, or we don't know what n is. And the common difference is 5. So in this case, we're going to subtract 3 from both sides. So I'm going to get 55 is equal to, expand this, that's going to be 5n minus 5. So we're going to add 5 to both sides. So there's 60 is 5n, divide both sides by 5, so that we see that in this case, n is 12. So in other words, this series has 12 terms in it that we need to add. So we're actually calculating for S of 12. So 3 plus 58 is 61, all over 2. So S of 12 is just really 6 times 61, which is 6 times 60 is 360. So this is 366. All right, so that was a little bit tricky only because we just had to do a little bit more work to actually determine what n is. But once we got n, we could just use our straightforward series formula. So in order to sort of practice this concept a bit, there's your homework, and we'll see you next time.